Hey guys, welcome to the last video in the basics of portfolio optimization. So to this point, we've been able to optimize 4 portfolios: our global minimum variance portfolio, our minimum variance portfolio subject to return constraints, our tangency portfolio, and the portfolio that maximizes the certainty equivalence of the investor. And we were then able to compare them to the market and the equally weighted portfolio within our sample period. But the real question in asset management and finance in general is predicting performance going forward rather than ex post optimization. So today we're going to replot our portfolios with the same optimal weights, but now we're going to project those weights onto return data, not from our sample period. So we'll be using the dates 2014 on. We've done all of the heavy lifting in terms of calculation in prior videos. So what I've done now is just copy down the variables we need to adjust. And I've just added zeros to all of these returns variables. And then from that, I've created a new returns zero variable that has been concatenated using these vectors of returns. It's the same exact process as before. We're just defining a new variable. And now we need to redefine the sample period. So prior to this, it was 2009 through 2013. And now we're going to be looking at the performance of 2014 going forward. So we simply just adjust the years and we use the return zero variable now. I've then gone ahead and calculated the portfolio statistics for the 47 industries as well as the excess return on the market. Now, knowing that we have the optimal weights, all we need to do is project those weights onto the daily return data from the 47 industries. So first we're going to assign the variable industry 2, and that's going to be equal to our new return sample period. And then we're going to subset using the iloc function, all rows, and then from 1 to 48 to include all of the 47 industries from our data set. And then we want to put the weights into a data frame so we can then multiply these matrices together. So we're going to use the pandas.dataframe function and then parentheses, bracket. We'll put in WG for the minimum variance portfolio weights. And then for the equally weighted portfolio, we're going to use the np.repeat function. And we're just going to repeat 1 divided by 47 times because it's equally weighted. That's pretty intuitive. And then we'll just include our other weights. So our W1 weights, our maximum certainty equivalent weights, and our tangency weights. And then finally, we want to multiply these two matrices together. As we always have, we've multiplied a transposed vector of weights by the industry returns. But now we're just dealing with 5 portfolios at the same time. So we're going to assign the variable all P4 for all portfolios in 2014 is equal to an MP.matrix. And we're going to put our industry return data in there. And then we're going to use a dot product or the at symbol and multiply it by a transposed vector of weights. The next thing we need to do is calculate the mean and standard deviation of these portfolios during our 2014 period so we can then compare them to the in-sample performance of the optimized portfolios as well as the performance of the market during our 2014 period. So we're going to start by assigning the variable all mu4 is equal to all p4. And we're going to take the mean of that and we're going to set our axis equal to 0, meaning we're summing column-wise, and we're going to multiply it by the number of trading days per year to annualize the figure. So if we return this code, you can see the return for our 5 portfolios has been added right here. And interestingly enough, that the return on the minimum variance portfolio was the highest during 2014, which may shed light into the low volatility puzzle. But let's first calculate the standard deviation. And we'll set that all SD equal to all P4. And just the same process, now we're taking the standard deviation, setting the axis equal to 0, and then we're going to multiply it by the number of trading days per year or the square root of the number of trading days per year. So we'll do DPY, and then we'll multiply this twice times 0.5 to take the square root. And if we populate this code, you can see the standard deviations has been added, but you can also see that the standard deviation on the global minimum variance portfolio is the lowest. So therefore, if it has the highest mean return and the lowest standard deviation, it's going to have the highest Sharpe ratio. So now we'll return to our plot and add these to our portfolio. I've gone ahead and added our new portfolios from our 2014 return data to a scatter plot, and you can see it below. It's the same process as before, but now I'm just subsetting the all standard deviation variable based on the row or the particular standard deviation from the portfolio I want to extract and then plot against the mean of that portfolio. So I think now we have the necessary information to compare our optimized portfolios in sample and the performance out of sample. So if we bring up our previous plot, first you can see that the optimized portfolios between the minimum variance portfolio, the maximum certainty equivalence portfolio, and our M1 portfolio have performed well out of sample. And on a risk-adjusted basis, they've beaten the market. The only optimized portfolio that hasn't beaten the market on a risk-adjusted basis is our tangency portfolio. So just based on looking at this information, portfolio G looks to be more robust than our portfolio T out of sample. And that's probably or likely because it's not as dependent or isn't dependent at all on fundamentally unreliable sample means. So in future videos, we'll go on how about maybe we can reduce this estimation error of our sample means. And just one last thing to note is that the equally weighted portfolio is performing worse than the market on a risk-adjusted basis. So this strategy to 1/n investing seems to be a bit of a fallacy. I've also gone ahead and added these portfolios from our 2014 sample period into the existing table that we've been working with. And just a couple quick things is you can see the Sharpe ratio on the global minimum variance portfolio is the highest outside of the sample, which is again leading us into this low volatility puzzle. And the tangency portfolio, which is supposed to have the highest Sharpe ratio, is very low in this case and even lower than the market Sharpe ratio. And this is again because the optimization is based on fundamentally unreliable sample means. And this type of analysis is great in Python because if you want to change the sample period that you're testing, we can easily change it. So if we want to see how these portfolios perform from 2014 to 2018, we can just easily change the sample period, and we can see that these optimized portfolios are starting to revert back to this cluster of the 47 industries, the market portfolio, and the equally weighted portfolio. So this is the end of the video section on the basics of portfolio optimization. In the next video section, we're going to start to rebalance these portfolios on a rolling basis and see if that increases the performance of our optimization. I hope to see you guys there.